What's up, guys? It's Mr. Brengle, and today we're going to be talking about UAPM Learning Sheet number 4, Constant Acceleration Learning Sheet 4. As you can see here, I've already filled out the answers, so if you haven't started this, I would strongly encourage you to try to answer these on your own really quick, and then come back and watch the video. But let's jump right into it. Part A says, where on the graph above is the object moving the most slowly, and how do you know? We know that the slope of a position versus time graph tells us the velocity of the object, so we want to look for the spots that have little to no slope. At points B and F, the object has little to no slope, so that shows us that the object is either not moving or moving the slowest, because every other point on this graph has some type of slope. Moving to B here, between which points is the object speeding up and how do you know? So once again, we want to look at the slope here, and we want to look for specifically for places where we go from not having a slope or a small slope to having a slope. And it doesn't matter whether that slope is positive or negative, as long as we have a slope that tells us that we have velocity. So from point B to C, we're going from no slope to having a negative slope. Which again just tells us that the object is moving in the negative direction with a negative velocity. And from point F to G, we can see that we go from having no slope to having a positive slope. So now the object has a positive velocity moving in the positive direction. C says, between which points is the object slowing down? So the opposite question. So we want to look for places where we go from having a slope to not having a slope. So from point A to B we see that, and then we also see that from E to F, where we go from a negative slope to having no slope here. D says, where on the graph above is the object changing direction and how do you know? At points B and F, that is where the object changes direction. We know this because initially the object goes in with a positive slope, meaning that the object is moving in the positive direction. And when it gets to point B, it then starts moving in the negative direction. It turns into a negative slope, so point B is one of the answers. And then point F, we go from having a negative slope going into point F, and then coming out of it, there is a positive slope. So at this point, the object changes direction. Page 2 here, you can see that I've already labeled some of the points here. We'll need that here in just a little bit, but we'll go ahead and answer this first question. Of course, I've already written it out to save some time, but we'll talk about it. So the written description of the motion here, I said the object starts at 25 meters and it's at rest, so there's no slope up here, and then it slowly speeds up as it goes down and starts moving faster and faster. I know this because we go from having no slope to having a negative slope, and that negative slope gets larger and larger as you go down. So that means it must be speeding up. It is moving in the negative direction, so we say the object starts from rest at 25 meters and it speeds up in the negative direction. Moving on to our motion map here, I'm going to zoom in quite a bit on this so it's easier for me to write. But we want to show that the object starts at some positive position. We don't have to, I'm not going to make you label it on here, but I'm going to start it, back here. So for the velocity, blue is velocity here up on top, blue. So this object starts from rest and starts increasing its speed. So we should be showing that these dots are getting further and further apart, and that the arrows are getting larger and larger, indicating that the velocity is getting larger and larger. And the object does end up back at 0 meters, so I want you to make sure that you at least have an arrow that gets to 0 meters. You can go past it if you need to. But this shows that our object is starting with a very small velocity, and then it's increasing over time, moving in the negative direction. So to show our acceleration vectors, we'll do that in red. We would want to put our dots in the same spots here. And then since the object is speeding up, we need our acceleration to be in the same direction of the movement, same direction of the velocity. So we will show that all of the acceleration vectors are pointed to the left, going with the motion of the object. and that those arrows should be the same length. Everything that we do in here in this unit is constant acceleration, so it's not changing. Okay, now let's look at, we'll need to use the graph for these next few. So it says find the displacement from 2 to 8 seconds. So you can see that I've already labeled the position at 2 seconds, or the coordinates at 2 seconds and the coordinates at 8 seconds in red here. Don't overthink this. Displacement is just the change in position. So when we're looking at change in position here, at 2 seconds, the object is at 24 meters, okay? And at 8 seconds, the object is at 9 meters, right here. So in order to find displacement, remember that displacement is delta x, which is the final position minus the initial position, which in this case is going to be 9 meters minus 24 meters. And that means our displacement is negative 15 meters. And displacement does have direction. That's what we use to calculate velocity, so that should make sense. Basically, going back and looking at this graph here, the object moves backwards by 15 meters during that time span. Okay. So part D, find the average velocity from 2 to 8 seconds. So in order to find the average velocity, we're on a position, we have a position versus time graph here. So the slope of a line on this graph represents the velocity. So what I would like to do is go ahead and connect 2 seconds to 8 seconds with this red line here. That line, the slope of that line is what represents the average velocity from 2 to 8. And since I've already written the points out here for us, we have the coordinates, we can go ahead and calculate that by doing the rise over run. In this case, it's going to be the final position minus the initial position, which we already did in the previous problem. That's negative 15 meters, over the change in time, which would be 6 seconds, the difference between 8 and 2 seconds. So let me come down here and I'm going to zoom in a little bit. So we want to do, so the average velocity, the average velocity is equal to the change in position over the change in time, and I just want everyone to understand that is the slope. Okay, so again, we already calculated the displacement. It was negative 15 meters. That was in part C. And then the change in time is 6 seconds, 2 to 8 seconds. And so that is going to give us an average velocity of negative 2.5 meters per second during that time span, from 2 to 8 seconds. So just to reinforce that, again, the slope of this line right here is negative 2.5. That represents the average velocity from 2 to 8 seconds. Okay. Now, moving on, part E, it's asking us to find the instantaneous velocity at 2 seconds and also at 8 seconds by finding the slopes of tangents. So if you guys remember, going back to a worksheet we did a while ago, the tangent line is the line that extends off the outside of this curve and just touches at 2 seconds on the outside, and it just touches at 8 seconds on the outside. That's what it's referring to. We did that activity where we found out that that tangent line is parallel to if we were to find the average velocity, or the time that we're interested in, so let's say we're going to find the instantaneous velocity at 2 seconds. So if instead we find the average velocity between 2 points where 2 seconds is right in the middle, so 1 and 3 or 0 and 4, that line will be parallel to the tangent line at 2 seconds. And that's important because that tangent line, since it just touches at 2 seconds, that means the slope of that tangent line will represent the instantaneous velocity at 2 seconds, the velocity of that object right at 2 seconds. So if we can just find the slope of a line that's parallel to that, where we already have the coordinates, which we happen to have here and here, that would be a much better option for us. So what I'm going to do is I'm going to go ahead and I'm going to connect these dots right here. So this blue line represents the average velocity from 0 to 4 seconds. And that is what we are going to use to find the instantaneous velocity at 2 seconds. So it's going to be hard for me to do, but if I could, I could show you. Let me try and do it here. So if I touch right at 2 seconds, which again I don't think I did. Yeah, I didn't do it very well there. But if I took this line, this looks about parallel right there. If I could take that and move it down, it would just touch right there at 2 seconds. So by finding this, the slope of this line, we're also finding the slope of this line. So I'm going to go ahead and get rid of that. But let's go ahead and move down here. And so what we're going to do, I'm going to change my color to blue here. To find the instantaneous velocity at 2 seconds, we are going to find the average velocity between 0 and 4 seconds. So the instantaneous velocity at 2 seconds is equal to the average velocity from 0 to 4 seconds. Again, we could also do 1 to 3 seconds, as long as 2 seconds is right in the middle. So those 2 points are, it's 0, 25, that's our first point, and the second point is 4 seconds and 21 meters. So if we use this, and we remember the slope of the line is the velocity, so that is going to be the change in position over the change in time, which our final position would be 21 meters. Okay, apologize, it's not working. So 21 meters minus 25 meters divided by 4 seconds minus 0 seconds. That is going to give us -4 divided by 4, which is -1 meter per second. So what that's saying is that the slope of this blue line up here is -1, meaning that the average velocity from 0 seconds to 4 seconds is -1 meter per second. Since that line will be parallel to the tangent line at 2, that means that the velocity at 2 seconds is -1 meter per second. Now, we can also do this for 8 seconds. I have chosen the 2 points at 6 seconds and, at 6 seconds and at 10 seconds, because 8 is in between those two. So I'm going to connect that line. That green line, again, represents the average velocity from 6 to 10 seconds, and that will be parallel with the tangent line at 8 seconds. So if we find the average velocity from 6 to 10, we will also be finding the instantaneous velocity at 8 seconds. So we'll come down here and I'm change over to green. Zoom back in. So the instantaneous velocity at 8 seconds is equal to the average velocity from 6 to 10 seconds. You could also have used 7 and 9 seconds. It's just what I chose to do. So again, we just find the slope of that line. We already had those points. The final position was 0 meters minus the initial position at 6 seconds, which was 16 meters, divided by the change in time, which would be 10 seconds minus 6 seconds. So that is going to be equal to -16 divided by 4, which comes out to be -4 meters per second. Okay, so hopefully that would make a little bit of sense, because as we go down this path here, the object is speeding up, right? So the average velocity from 0 to 4 seconds should not be as great as the average from 6 to 10, because this object is accelerating and it's speeding up the whole time. So up here, its average velocity is -1 meter per second, and then here it's -4 meters per second. Okay. Now, this is also asking us to solve for the average acceleration from 2 to 8 seconds. And we really needed to find the instantaneous velocity first in order to do this question, because the equation for finding the acceleration is the change in velocity over the change in time. So that's just taking your final velocity minus your initial velocity and dividing it by the final time minus the initial time. Well, since we just solved for the velocity at 8 seconds, which is our final velocity, that would be -4 minus the initial velocity at 2 seconds, which is -1 meter per second. So we're subtracting a negative number, which means that we will end up adding these together. And then our time difference here is 8 seconds minus 2 seconds. So this will end up becoming, so -4 plus 1 is -3 meters per second divided by 6 seconds. So that is going to give us an average acceleration of -0.5 meters per second squared. Now, last question. It says instantaneous velocity at 5 seconds. So you could do this the long way, which would be to come back up here to the graph and calculate the slope from, say, 0 to 10 seconds, where 5 is in the middle, or from 4 to 6 seconds. Or you could just remember that we already calculated the average velocity from 2 to 8 seconds, and 5 seconds happens to be in the middle of that. So since 5 seconds is the midpoint between 2 and 8, the average velocity from 2 to 8 will be equal to the instantaneous at 5 seconds. So this is your answer, -2.5 meters per second. And that will conclude the first 2 pages of Learning Sheet 4. I am going to do the next 2 pages in a separate video.